Well, hey there, AP Physics. It is time to start our new unit. We are going to be taking a few days and doing some basics with forces, and then we will head into the math a little bit later. So, as we go through this, I'm going to ask Doc to stop every once in a while and show a video clip, and I've got all that ready to go. So, hopefully, you guys are ready to go too. If I end up going too fast, obviously, you can go back and find these videos again, but we're going to give this a whirl. Here's our new unit. This one is where some of you general guys, you're going to get some stuff you haven't seen before. All right, it'll look normal for a bit, but then we're going to get into some complicated stuff. But before I terrify you all, let's start with some of the basics. All right, so let's start off with what the heck is a force. Now, generally, what most folks tend to say is that a force is a push or a pull. What I like to say is that it is an interaction between two objects. All right, so you've got two objects interacting with one another. And sometimes those objects are touching and sometimes they are not. So we have what are known as contact forces and field forces, or, big surprise, non-contact forces. All right, so let's give you some some definitions here, or some examples here, I should say. Let's start with field forces. These are for things that are not touching. And our biggest one that we deal with the most is gravity, the force of gravity. You can have two objects far, far apart, like the sun and the earth, and they are attracting to one another. That is definitely one of our field forces. All right, so gravity. Magnetism. I don't know about you, but when I was a kid, this was like one of my favorite toys. You know, getting a couple magnets that can still be easily distracted with a refrigerator magnet and seeing how close I can get the magnet to the fridge before it starts tugging on it, but I'm obviously not touching there. Then we've got some static electricity or electric force, I should say. Also a fun one. And stronger. Here's the thing, too, guys. Keep in mind, these are both stronger than gravity, but gravity wins. Gravity rules the universe. And the reason gravity rules the universe is because every two objects, any two objects, will have a gravitational attraction. Magnetism, let's face it, you need to be made out of iron or nickel, that sort of thing. Not everything is. For electric force, you generally have to have an imbalance of electrons, and most objects don't. So gravity wins, even though it's the tiniest one. Contact forces, key ones that we look at here. Tension, which is a force along a rope or a string or a rope or a chain. That kind of a force. A friction, and we've got a couple flavors of friction. We'll talk about friction in great detail a little bit later on. And then we have what we consider to be normal forces. And this is actually a mathematical term, and it means perpendicular. It's a force that's perpendicular to the surface, and we're definitely going to talk about these. I also like to call this the crunchy force. If you are crunching on something, if you're pushing on it, this will be the response that comes back. When the atoms get crunched, this will be the push back. And those are, let's see, 1, 2, 3, 4. Oh, last one, spring force. Guess what? You need to have spring for this one. Now, we're going to get into a little more detail about these, so for now, just classifying them is probably good enough. Now, depending upon what kind of a textbook you're using or what kind of a question you're reading, sometimes people talk about oh shoot, the words are escaping me. I'll remember a little bit later on, like a contact, like a push force or applied force. I usually classify those as normal forces myself, but not to worry, not to worry. I think they're usually self-explanatory as we go. All right, the unit of force is called the Newton. I'm pretty sure you know it's not named after Fig Newton. It's named after Sir Isaac. All right, a Newton is defined mathematically. Well, first of all, it's capital N. That's what we like to write. But if you have to know what it's equal to, it's going to be equal to a kilogram times a meter per second squared. All right, and you'll see that that fits in rather nicely with what we are doing later on. Okay, let's move on to the next page. Here we go. Alrighty, so let's talk about the different types of contact forces that we have. F sub g, otherwise known as gravitational force. Now, direction. Take a second and think to yourself, what is the direction of gravitational force? Probably most of you said down. And most of the time I would agree with you. But let's consider this. Let's say that's the Earth, and there's you, obviously not to scale, right? And we'd say, okay, the gravitational force is down. But what about when the Earth turns and you're over here? I don't know what happened to your arms there, right? But if down is where the force is, you're going to fall off the planet, and we know we don't do that. So it's this way, isn't it now? Inward, in towards the center. Now, granted, most of the time, that's exactly where we are. And down is the way we're going to define that on a piece of paper. But do keep in mind, it's towards the center of the planet. And gravity does exist between any two objects. But in order to be really noticeable, you need to be at least the size of a planet. You need to be really, really big. Otherwise, let's face it, if gravity were that strong, everything would fly off your desk and whack you in the head. And that would be distracting. So let's not do that, all right? So towards the center of the planet, when is it present? Always. Always. We're not going on any field trips out into outer deep space. Okay, now you might say, oh yeah, well, I will be, there's no gravity when people are floating out in space. And I would say, no, that is not correct. All right, that is not true. There is gravity. In fact, gravitational force and therefore eventually gravitational acceleration, little g, 9.81, is not noticeably changed unless you are at least an Earth's radius away, which is a little bit different than probably what you've been taught. You've probably done some of those chemistry questions along the lines of where do you have the most weight or the most gravitational force, in the center of the Earth or at the top of a mountain. The truth is it's identical. It's so close, it's not worth mentioning, all right, because you have to be really far away from the Earth's surface for it to make any difference. And if you're out in space, there's always going to be some other giant thing out there that you could be attracted to, but it takes a lot for you not to be attracted to the planet. Now, the thing about being weightless, which we usually are all talking about, it's actually a function of what we call normal force, Fn. I don't know why I put that in quotation marks. It doesn't need quotation marks. Right? It's called the normal force because it's perpendicular to a surface. So, for example, here's me, and let's face it, that's what my hair looks like right now. So I'm feeling better because my surgery is over. Right? Here I am. I'm on the ground. Right? I have gravity pulling me downward. And because I'm pushing on the floor, I am going to feel a normal force going back up to me. Right? So how do I get weightless? Well, all you have to do is take the floor away. Right? So what we consider, what we perceive, I think I spelled that wrong. I think it goes the other way. Anyway, whatever. Spell police, you get me. All right, what we perceive as weight, it's really the normal force. The easiest way to make me weightless is to cut a hole in the floor. Right? As soon as I start to fall, I'm going to be weightless. But I'm not weightless because I'm falling down towards the center of the Earth. Okay? So let's keep in mind, normal force is important for us to consider ourselves weightless. So when you talk about somebody in space, in a spaceship floating around, and you say, oh, it's because they're weightless, that's not true. It's because there's no normal force. And the reason there's no normal force is because here's the ship, I don't know why it looks like a piece of bread, but it does. And here's the person, right, with no legs, and they are falling because they don't have a floor beneath them, because this is falling, because the space station, is also falling at the same rate. It's being attracted at the same rate towards the Earth. So because of that, they're not touching the floor, and you think they're weightless because they're floating around. But it's not really weightless. It's no normal force. So kind of keep that in mind. Normal force, like we said, is always perpendicular to your surface. So if you're standing on the floor, like we said before, gravity is going to go down, normal force is going to push back up. But if you're standing with your back on the wall, here's the wall, gravity is still pointing you down. Normal force is now going this way because it's perpendicular to the surface. So keep that in mind as we go. You always have to go perpendicular to the surface. If we've got something that's on an incline, gravity will still always go straight down, but normal force will go perpendicular to the surface. So normal force can go in a whole bunch of different directions, and that's really important as we go along. But again, it's a responsive force. I mean, think about it this way. When I push down on the floor, if the floor didn't push back up equally on me, I would be falling through the floor, wouldn't I? And I'm not. So I know that these two have to be the same, and that's what we consider to be a balanced set of forces. More on that to come. All right, so we looked at gravity, we looked at normal force, a couple of other ones. What did we mention? Spring force. Okay, in order to have spring force, guess what you got to have? A spring. Woohoo, that's mind-shattering right there. All right, so spring force, if you pull on a spring, like let's say your spring is like this, right, and you pull this way, which way does the spring want to go? It wants to go back this way, right? This is the direction of the spring force. It wants to restore. So the direction of a spring force is, let me fix that, hang on a minute. Let's do that. All right, so the direction of a spring force, it's along the spring, whichever way will restore it. Okay, so we've got a bunch there. All right, it's going to go along the spring whichever way. So if you pull the spring and you make it get bigger, the restoration force will be in the opposite direction. If you compress the spring, it's the same thing. You're going to restore it in the other direction. Okay, the more you pull it, the more force you have. Obviously, we'll talk definitely more about that in a bit. Just in case we need it soon, let me give you this formula to go with it. Okay, this is also known as Hooke's law. The force of the spring, that's right there. These two bad boys, this is called the spring constant. And it is specific to a spring. It's kind of a matter, it's a measure of how stiff the spring is or its stretchiness. It's measured in newtons divided by meters. This little guy right here, that is the stretch. Not the length of the spring, but the stretch. And the stretch is also in meters. A lot of times you got to do some converting on that. Okay, so that's that one. Last one, and also quite important, is friction. And we'll spend some time specifically on friction in a bit. All right, this is a parallel force. It's a shearing force. Right? It's parallel between the two surfaces. I'm going to give you a formula here. It's not going to mean a whole lot right away, but we will get to it a little bit later. This one is called mu. That is also known as the coefficient of friction. This one, force of friction. This one is the normal force, obviously. Okay, so the main thing about friction is it runs parallel to the surfaces versus normal force, which is perpendicular to the surfaces. There's two flavors of friction. We have what's known as static friction And we have what's known as kinetic friction, and the names hopefully give you an idea of what we're talking about. This is when you're in motion. Let's say in motion. This is when you're at rest, but it doesn't always exist when you're at rest. Okay, this one is always greater. It always takes more effort to get something moving than to keep it in motion. All right, if you are in Walmart and you have a shopping cart and you fill it with like 50-pound bags of dog food and a whole bunch of gallons of milk, you know if you need to get rolling, it's going to take a lot of pushing. That's because your static friction is far greater. But once you start to roll, you know your kinetic, you're going to be able to keep in motion pretty well. So you're actually like yelling at the little old ladies in the aisle to get the heck out of the way before you run them over because you can't stop the cart. That's because your kinetic friction is much less. All right, so there's a lot to flesh out here beyond this, but this is a good beginning, at least about types of forces. All right, so the next thing I want to take a quick look at, and then we're going to look at some videos. All right, it's going to be Newton's laws. So Sir Isaac has 3 laws that basically govern motion overall, and the whole idea is that if we have what are known as balanced forces, actually let's just skip that. Let's just skip that for now. Okay. Yeah, let me think about this. How do I want to do this? Okay. Newton's 3 laws you've probably learned from middle school. All right, so we're going to just list them quickly for you here. The first one is sometimes called the law of inertia. All right, now you've probably heard this one: an object at rest will stay at rest, an object in motion will stay in motion unless acted upon by an outside force. I'm going to phrase it somewhat differently. All right. So if you have balanced forces, your objects are going to move or act with a constant velocity, meaning if they are at rest, they will stay at rest. If they are in motion, they're going to continue to move with that constant velocity. But when you have unbalanced forces, the velocity is going to change. So for example, right, in general physics, and if for those of you that were in general physics, you'll remember this, we have the little hover disk, right? It was that little battery-powered soccer ball looking thing, right? And we took it, and there's a little bit of air that goes underneath it, right? And so you turn it on, and then we would push it, right? And push it and pass it back and forth. And what would happen is it would move, right? And I'm trying to make these evenly spaced apart, like a motion map or an oil drop diagram, right? But here goes your hover disk, right? And it just continues to move until eventually somebody touches it and then pushes it back, and then it starts to move back this way, right? But as it moves, when nobody's touching it, it moves with a relatively constant velocity. Now, what I do after that is we say, hey, what forces are acting on the hover disk at this point in time? And what I always get in the end is, first one's going to be gravity, right? And these are what are called free body diagrams. This is supposed to represent my hover disk, this little dot. All right, so gravity is going to be pulling it down. What's pushing it back up? There's got to be something. It's normal force, right? Because it's crunching the floor. So those are my 2 forces. And I say, hey, does that look balanced or unbalanced? Oh, that looks balanced, Mrs. Grady. Why? Because I have 2 arrows and they're about the same size and they're going in opposite directions. So those look balanced. And if they're balanced, what this tells me is that this is going to move with constant velocity. Right? So they say, oh yeah, when it was moving across the floor, nobody was touching it, and we took a snapshot of it. We're not looking at it over a long period of time. We're taking a snapshot. So it's moving, nobody's touching it. Here it is, right? And it's just cruising along here, headed to the right. and nobody's touching it. These are the forces acting upon it, and it's moving with a constant velocity, right? And I say, hey, consider the same hover disk when it's just sitting on the floor. And lo and behold, they come up with the same example here, right? So this is moving. And then I say, hey, let's take a snapshot when it's just sitting there and it's not doing anything. And imagine this, we get exactly the same diagram, right? And I say, is that constant velocity? Oh yeah, it's not moving. It's constantly zero, right? So these are, again, balanced forces. The ones pointing up equal the ones pointing down. They're about the same size. All right, so this is also what we would consider constant velocity. It's at rest. And anytime we have forces that are balanced, now I could have 2 arrows or I could have 4 arrows, whatever, but as long as it's balanced, we have a constant velocity. And that's what Newton said as well. He said if forces are balanced, they're going to act with a constant velocity, but when forces are unbalanced, the velocity changes. So consider this. One of the next things we do is we try to do the hovercraft. Actually, let's make it look like the hovercraft, right? So there's my hovercraft. And instead of the air, we say no air, we turn it off. Actually, let's redraw the whole darn thing, shall we? All right, so here's my hovercraft, and I say, all right, guys, so we forget to turn it on and we give it a push. And while it's moving, but before it stops, what happens? Take a snapshot, and they say, oh, okay, it's slowing down because of friction, right? It doesn't work very well when the air's not on. Friction slows it down. So I tell them, hey, draw me a free body diagram. And so they do, right? Dot in the middle, gravity's acting going downward. Notice we make a lot of these little diagrams. Gravity's going up, or normal force is going upward here, and then they usually put friction, and they can put it on either side. It doesn't really matter to me right now, right? But here goes the friction. And those are the forces acting on the hover disk. And I say, hey, you know, is that balanced or unbalanced? And I say, oh, it's unbalanced, Mrs. Gray. Look, there's a third one there. And it doesn't have anything on the other side. So that is unbalanced. What's happening in here? Oh, we're slowing down. Well, that's a change in velocity, isn't it? That's an acceleration. And that's what an unbalanced force will do. It changes your velocity. Now, we could go faster or we can go slower. We can change direction. We're not going to worry about that today. But that's what unbalanced forces will do. So that was what Newton called the law of inertia. So what the heck is this giant term inertia? That one comes up a lot. And all that means is that it's a resistance to changing. Whatever your object is doing, it wants to keep on doing it. Now, I mean, I'm talking like it's got, you know, comprehensive thought, but it doesn't. Whatever motion it's in, it wants to stay there. The only way it's going to change that motion is if there's an unbalanced force, like this guy over here, this situation. All right, the larger the object, the harder it is to change it. And when I say larger, I'm not talking volume, I'm talking mass. All right, the more mass an object has, the harder it is to change. And any of you who play any sort of contact sports know this, right? Larger objects harder to change their motion. If you are trying to stop someone running forward on the line in football and they are giant and you are not, it is very tough to do. Even if you are not giant, it's tough to do. All right, because they have a giant inertia. So as soon as they are in motion, they are going to continue in that path unless something slows them down. And it's going to take a very big force over here, a big force to slow somebody down who has a lot of inertia. And that's something at rest or it's something in motion. What I'm going to do now is I want you to stop the video and I want you to watch one of my favorite little video clips. It's called shopping cart inertia, or at least that's what physics teachers call it. And I want you to take a look at what happens, and I'm sure Doc is going to explain exactly what it is that is going on there. So I'm going to pause for a moment, and you guys can watch the video on YouTube and discuss it a little bit. Hopefully you enjoyed that. All right, let's take a look at Newton's second law. And I mean, I just cracked up. I love the, did you notice the lady who like stops and looks and then walks away because it's not her job? Cracks me up every single time. And their faces, those guys, their faces, oh my goodness. Like, oh no, What are we going to do? All right, Newton's second law. I spend the least amount of time going over Newton's second law because we use it so much that eventually it becomes intuitive. All right, what this is saying is that whatever your net force is, meaning your unbalanced leftover force, is going to be equal to mass times acceleration. Now that looks very simple as you go along, and there's some really important relationships here. Like, for example, anything on opposite sides of my equal sign has a direct relationship. Whoops, not MA. What am I doing? Let's try that again. All right, if the force goes up, if the mass goes up, the force to move it will go up at the same acceleration. We're, of course, keeping the acceleration constant here, right? We have a direct relationship here. We have the same direct relationship with acceleration if the mass is constant. Now that's the most likely scenario, right? That the mass would remain constant. And then anything that is on the same side, for example, mass and acceleration, is going to have an inverse relationship. And I can tell that just because I'm looking at the math relationship going on here. I'm just looking at that 3-variable formula, and this is for any 3-variable formula, so this isn't that big of a deal. However, this small notion of F equals ma, in order to get us there, that can be incredibly complicated. All right, now sometimes I get from folks, what the heck is the net force? Like, how can you define what net force is? And I often say, hey, do you have a part-time job after school? Do you ever get a paycheck for something? Right? If you look at your paycheck, you get what's known as your gross pay, which is like, let's say you make 10 bucks an hour and you work for 10 hours. You say, yeah, that was pretty good. I made $100. But your paycheck doesn't say $100, right? Because they're going to take out Social Security and they're going to take out FICA. I don't even know what FICA is supposed to be. There shouldn't be an arrow. There should be a minus. Sorry. But I was joking, like, do you know what FICA is? I know that has to do with the Social Security insurance and all that kind of stuff, right? But they take out all this stuff. And in the end, the federal tax, the state tax, all that good stuff. And in the end, you get what's considered your net pay. And I joke that's usually about, $5 when you're all done. It's not true, but you know what I'm saying, right? So you might gross make 100, but in the end, your net pay is only going to be 5. So it's the leftovers after you take out all the stuff. Right? And that's kind of what net force is too. It's the leftover force when you subtract out all the ones, like one's going to the left and one's going to the right. Okay, they're going in opposite directions. We know they're vectors. We better subtract them. That's what net force is. It's the leftover force when you account for everything. Okay? So, not to worry, but my point is when we work with F equals ma, it sometimes takes us a really long time to get there because there's a lot of steps in between. So I'm just going to leave it at that for now. We're going to spend a lot more time with it later. That's going to take us to Newton's third law, otherwise known as N3 to physics teachers usually, right? Newton's third law. For every action there is an equal and opposite reaction. You've probably heard this one before. And you're like, yeah. But this one is actually really, really profound. I mean, if you don't account for Newton's third law, you can really get messed up. And you know who forgot to take care of Newton's third law once? These guys. They're supposed to be the smart guys, and they messed things up. And so I have another video clip here, and I want you to take a look. And take a look at how NASA almost killed somebody because they forgot about Newton's third law. And I'm not lying there. Okay, so take a minute, look that video over and take a look at how that works, and then I'll be back. Okay, last but not least, did you like that video? And it's funny, that particular spacecraft they have in there, I went once to I went to Chicago to one of the museums. I forget if it was, it's in that campus downtown, and they actually had that particular structure, that particular spacecraft in there. And I remember looking at that thing, and first of all, it looks like someone took the tinfoil out of my kitchen and wrapped it up. And I was like, really? They sent a guy into space into this thing? But the second thing that I really noticed was that, I mean, it's about the size of a lazy boy recliner. And they stuck two guys in there for like however many days and shot them up into space. And I just thought, heck to the no, I would never, ever do that. These people had to be crazy. And then not only that, they get them inside the little tinfoil can. Now you're going to like step out of there and go start doing work out in space. And then you almost kill the poor guy. Ah, wouldn't have been me. That's all I can say. They were braver than I would ever, ever be. So consider that. I mean, these guys have really, they put a lot on the line when they went out there. They really trusted in NASA, and sometimes, not so good. Kind of let them down a little bit. But luckily, we all figured it out after that, right? We, like I had anything to do with it. But NASA figured it out after that. Alrighty, so Newton's third law. Here's the main thing. It's like we say things along the lines of, oh, well, if there's a horse, and I know, there's my horse. I don't know what that's supposed to be exactly, right? But there's my horse. Wait, we better give him 4 legs. Okay, and no comments, people. I don't want to hear about it when I get back. All right, so we all know I'm no artist. I never claimed to be. All right, so there's the horse, there's the wagon, right? So here goes the horse, and it's pulling this way. We say, oh, the horse pulls on the wagon, and then the wagon pulls back on the horse with an equal and opposite amount, like 100 newtons this way, and this guy's going 100 newtons that way. Well, how can the cart ever move? And that was always the giant paradox, right? Here's the thing. You got to focus on what the forces are acting on, okay? So if I want to focus on the horse, ooh, look at that red. Who knew I had red ink coming at me, right? All right, if I want to focus on what's going on with the horse, then this 100 newtons matters, right? If I want to think about what's going on with the wagon, this 100 newtons matters, okay? So before we get paralyzed into thinking that we can never move, because we know we do, all right, it has to do with what the objects, what the forces are actually acting upon, all right? We got to be very specific. When we talk about what's happening to the wagon, we do not care what is happening to the horse. We forget about the horse. We only think about the wagon. We say, oh yeah, well, it's getting pulled on with 100 newtons, and then we don't care what the heck's going on with the horse after that. All right, so keep that in mind as we go. It will come up. We will worry about it a little bit more. But these two guys here, the horse and the cart, we call these action-reaction pairs. And I will definitely be bringing them up, especially when we start talking about things moving in a circle and why we have no such thing as centrifugal force. All right, I think that is plenty for one day. My goodness, that was 32 minutes, probably longer with the videos and stuff. So we're going to have you all relax. You do have WebAssigns 1 through 3 that will be due. Gosh, where's my calendar? They're going to be due on Wednesday, the 18th. So definitely number 1, it's mostly conceptual stuff like this. So you're good to go. All right, back at you tomorrow.